Okay, so with much of the math behind us and system level stuff behind us, we are now venturing out into circuits. Okay, now this is where all the stuff that we have learnt about so far, we are going to start implementing, and we are going to start building amplifiers and devices, okay, and circuits. So the first block, as I mentioned, that we will be looking at is a low noise amplifier. Okay, the LNA is a very critical block in any receiver, and as we have seen in the freeze equation, the first block which touches the RF signal should have the lowest noise figure as possible. Okay, because that is what is going to limit the overall noise figure of your entire receiver chain, because all the subsequent blocks are going to get decimated, or the noise figure of those second, third and fourth blocks are going to get divided by the gain of the preceding stages. Okay, but the only noise figure which does not get divided is basically the noise figure of your first stage, which usually turns out to be the LNA. Okay, of course there are instances where you use a band pass filter, and we also saw the necessity of making it as low, as low loss as possible, because loss is equal to the noise figure, and even in that case, directly, the noise figure of the LNA gets added, or rather amplified, by the loss of the band filter. Okay, all right. So now, as we start looking at a low noise amplifier design, it is important for us to get ourselves familiarized with the devices that we are going to work with. Okay, now in the typical microwave circuits course, you would have looked at, there are different devices that are typically used. You'll definitely have some types of FETs, but mostly you'll be looking at silicon germanium bipolar devices, or gallium arsenide FETs, or gallium arsenide transistors. You'll also be looking at some HBT transistors or HEMT transistors, different types of transistors, right? But in this course, we are going to exclusively look at CMOS because of its huge advantages. As I mentioned towards the, I think mentioned in probably the first class, these devices are much more expensive than CMOS devices. Okay, CMOS devices are much cheaper, and the entire CMOS process, although the overall cost is very high, but because of the volume production, the cost per unit IC becomes very, very cheap. Okay, which is why the entire VLSI industry is now sitting with CMOS. All digital circuits predominantly are done only in CMOS. Okay, and in analog circuits, a large majority have moved over to CMOS. Mixed signals are in CMOS. RF circuits are the ones which are the late entry ones, and of course there are some niche applications both in analog as well as RF applications where you still use silicon germanium or or other types of devices, but now the world is moving so much more towards CMOS devices, even in RF domain. In fact, all your Qualcomm SoCs or your Samsung SoCs or Huawei SoCs, or even for that matter Apple SoCs, the RF transceiver is all in CMOS in your mobile phone. Okay, so only the final stage, let's say the power amplifier or some switches, are made in other technology nodes, but otherwise it's all in CMOS. So let's get ourselves familiarized with CMOS. I know our VLSI students here will get super irritated if I draw the CMOS structure once again. But since it's a mixed class with both the BTech and the MTech RF students also present, I just want to have a very quick overview of the device behavior. Okay, so I hope all of you will know at least some parts of it because of the courses you have taken earlier. But I hope this will be a quick recap of the device behavior, and we will be able to proceed from there. Okay. Now the large signal behavior we know. So a MOSFET, an NMOS is drawn like this, a PMOS is drawn like this, right? The typical convention is where you have the arrow is the source, the other terminal is drain, and this is the gate. So here this is the source, this is the gate, and this is the drain. So this is your NMOS device, this is your PMOS device, right? Now, the direction of the arrow shows the current direction also. So the drain current basically flows in this direction in an NMOS. Okay, current flows from drain to source in an NMOS, and in a PMOS, the current flows from source to drain, right? And unlike a BJT transistor, here the drain and the source can be interchanged. Okay, so in a BJT transistor, you had what? Draw it properly. Yeah. So this is an NPN transistor, and you had a PNP transistor, right? So here again, it is very similar. You can see the similarity, right? So here you cannot interchange the collector and the emitter. Okay, C and E cannot be interchanged. Whereas here, drain and source can be easily interchanged. In fact, I have showed you the cross section, and from the cross section, it is easy to see that the drain and the source are symmetric, and therefore drain and source can easily get interchanged. Okay, and the typical convention is for an NMOS, the higher potential is basically the drain, and for a PMOS, the higher potential terminal is your source. Okay, so for a NMOS transistor, if one terminal, okay, apart from the gate, okay, between the drain and the source, if one of the terminals sees a higher voltage, that is the drain, and the other terminal is the source, and it's exactly the opposite for a PMOS device. Okay, now the region of operation, there are three regions of operation, right? Where basically this is a gate controlled device. So the gate to source voltage, if it is lesser than the threshold voltage, right, the drain current is 0. This is for an NMOS. And for a PMOS, you can always say a very easy way to handle PMOSes is just invert the subscripts. Okay, so VSG should be greater than, sorry, if VSG is lesser than mod of VTHP, ID is 0. Okay, so what is the source voltage? This is the source gate voltage, sorry, VSG. For a PMOS, it is the gate to source voltage, VGS. Okay, now in RFIC circuits, many times you'll use so much of NMOS devices, and only in some cases you'll use CMOS devices. But anyway, let me just cover it quickly so that you are very comfortable with these things. Okay. Now, typically, if you look at the PDK of any or the model file of any NMOS or a PMOS, you will see that VTH is a positive value and VTHP is a negative value, which is why I have written modulus of VTHP. Okay. Now, this is what is called as the cutoff condition, where the device is off, the transistor is off. Okay. Now, the device is on or it is operational only for a VGS greater than threshold voltage, or in other words, VSG greater than modulus of VTHP. Okay. So, for example, in a 65 nanometer device, the threshold voltage is somewhere around 350, 380 millivolts. Let's say VTH is, let's say, 380 millivolt, and let's say VTHP is, let's say, minus 400 millivolt. Okay, just an example. Okay. Now, if you take a transistor, let's say you ground the source of the NMOS. If the gate of the NMOS, if you give the gate voltage to be greater than 380 millivolt, okay, what the drain current starts flowing. All right, and in this case, usually the PMOS hangs from the supply. Okay, the supply for a 65 nanometer technology node is 1.2 volts. So please keep this in mind. For all your projects and assignments, your supply voltage has to be 1.2 volts. Don't put very high voltages. Okay. So this is the recommended supply voltage for a 65 nanometer technology. The only exceptions seem to be are power amplifiers, where you do some stacking and you increase the supply voltage. But apart from that, for all other circuits, okay, VDD is only 1.2 volt for this technology. If you go to 40 nanometer technology, 28 and so on, VDD is 1 volt, and typically it comes down to even 0.9 and so on for 16 nanometer FinFET devices or 22 nanometer devices, usually the VDD is around 0.9. Okay, so the lower the technology node, the lower the supply voltage also. If you use a 180 nanometer device, you have 1.8 volt supply and so on. Okay. Now coming back to this one, let's say this is 1.2 volt. Your VG here should be lower than what? 0.8 volts. So that you have basically 400 millivolt of gate to source or gate voltage here. Okay. Now this is what is the ideal behavior. Let me add a note. If you plot the VGS and versus ID, which is what is typically called as the input characteristics of a transistor, this looks very similar to your BJT or your diode. Okay. Only thing is the equations are different. Okay. Now you will basically see something like this. Okay. This behavior is quadratic. All right. And it is not exponential. For a BJT or a diode, you have e to the power of VBE by VT or something like that. VBE by VT for a BJT, VD by VT for a diode, and it is e to the power of something, e to the power of that. Okay. But here you do not have e to the power of VGS. The device behavior in this region is given as ID is equal to mu n Cox W over L. Okay. So there are two regions of operation. So let me come to that. Then I will write the equation. Okay. Just let's take it as being quadratic behavior. Okay. Now you can see that the threshold voltage is somewhere here. Okay. Something like this. Okay. Now this, you can also see that below the threshold voltage there is a smaller amount of current which is flowing. Okay. So that is what is called as subthreshold conduction. And this is more pronounced in lower technology nodes. When I say lower technology nodes, let's say 1P, 90, 65, 40, 28, 22, all these more advanced technology nodes. In lower technology nodes it is more. Okay, subthreshold conduction is more, which is why in digital circuits you talk about leakage power and so on. Okay, so anyway, let me not get into that. So there is subthreshold conduction. The current does not drop down to complete zero. Probably some 20 years back, the devices that they were using, probably the 1 micron device, 350 nanometer devices and so on, it will come down, significantly come down. Okay, the current will really come down much lower. But here in 65 nanometer and so on, it doesn't come down so significantly. The I-on by I-off ratio is not so much. Okay, all right. Now once the device is, let's say, quote unquote on, all right, there are two regions of operation. Okay, so now the current is now going to depend on the VDS, okay, ID. So the setup for this is something like this. Let's say you give a certain VGS, okay, let's say you give some 0.45 or something like that. Okay, and now what you are going to do is you are going to sweep the drain to source voltage. Okay, now when the drain to source voltage is 0, you don't have any current flow. Okay, so the starting point of this curve is basically here. All right, for VDS is 0, the current flow is 0. Okay, now as you start increasing the VDS slowly, the current starts increasing linearly. Okay, now after a point, what happens? The current starts bending and then the current starts saturating. Okay, so ideally it is supposed to kind of going to saturate. Okay, now for different values of VGS, let's say this is VGS1, this is VGS2, which is greater than VGS1. Let's say this is VGS3, which is less than VGS1. You will get curves like this. This is what is typically called as the output characteristics curve. All of you would have studied this in your analog electronics or your device course, right? Now, this region of operation, okay, this region of operation is what is called as the linear region, or it is also called as the triode region, okay, where the current is directly proportional to the VDS that is applied, and therefore ID in triode the current equation is something like this: mu n Cox W by L VGS minus VTH into VDS minus VDS squared by 2. All right. So this is your, I mean, for very small values, VDS, this term goes off. Okay. Very small values, it's a linear function of VDS. Okay. And then as you go to this region, let's say this is the second region, you get the whole term. All right. Now beyond this point, this is the point where it occurs what is called as pinch off. Okay. So pinch off basically occurs where VDS is equal to VGS minus VTH. It's very simple to understand. Now what happens is, this is your gate voltage. Let's say this is source is grounded. You have VGS like this. Now you have VD. Now for very small values of VD, right, VGD is almost equal to VGS, right? So the channel that is formed is pretty much like this, right? Now as VD or VDS increases, what happens? VGD decreases, right? So now the channel starts moving like this. Okay, the channel starts funneling out at the drain end. At the source end, it is the same. Okay. Now beyond a point, there comes a point where the channel gets completely cut off here, or in other words, the channel is pinched off when VGD is less than or equal to the threshold voltage. Now VGD can be written as what? VGS minus VDS equal to threshold voltage. Okay, and the channel is pinched off for VGD lesser than or equal to threshold voltage. Okay, so if you use this inequality, you get VDS greater than VGS minus VTH. Okay, so this is basically your pinch off condition. Okay, so for VDS greater than VGS minus VTH, okay, the current saturates, and the current equation is given by mu n Cox divided by 2 W over L VGS minus VTH the whole square. Okay. Now ideally you don't have any dependence on VDS beyond it, but as nothing is perfect in the world, this has a certain slope. Okay, and this slope is what is called as the output impedance, right? That 1 over that slope. So this slope is what? Dou ID by dou VDS. Inverse of the slope is what is called as a parameter called as R0. Okay, and to include that effect, we can say mu n Cox divided by 2 W over L VGS minus VTH the whole square into 1 plus lambda VDS. Okay, lambda is a constant. Okay, which says that the current slightly depends on VDS, and this lambda shows you how much this dependence is going to be. Okay, so as you go to lower and lower technology nodes, this becomes, this curve starts becoming more and more steep. It doesn't become very saturated. Okay. Now the same thing for a PMOS, you can say VSD is greater than VSG minus modulus of VTH. Okay, this is the condition for saturation region. So this region is called as saturation region. This is for a PMOS, and for an NMOS, it is VDS greater than VGS minus VTH. Okay. All right. So this is a very quick overview of device. Now we can look at what is called as the small signal model. So let's look at what is the small signal model. Whatever we looked at till now is what is called as the large signal model, right? What is called as a small signal model? So the notion of small signal means there is a small, let's say this is an amplifier. Okay, this has a certain bias voltage. Okay, or let me not use an amplifier. Let me just use a device. Okay, an NMOS. I'll just explain using an NMOS. Now gate voltage can be written as a sum of a DC voltage, a DC bias voltage, and a small AC voltage. Okay. So now VGS can be written as VDC plus VAC. Now the approximation of a small signal holds good if the magnitude of VAC is much lesser than VDC. Okay. A small example, let's say VDC is 0.45 volt, and let's say this is going to be some 1 millivolt sine omega t. Okay. Now if you plot this, how will this basically look like? This will look like, this is my 0.45 volt, and on top of that it's going to be a small sinusoidal voltage, okay, which let's say goes up to 0.451, and this is going to be 0.449. This is an example of a small signal voltage. Okay, so it can also be like 10 millivolts and so on, but basically if your signal is very small when riding on top of the DC voltage, it is approximately used, it is called as a small signal, and we can understand the behavior of the device for the small signal. Okay, the behavior deviates as you keep increasing the thing, but that's a different thing. Okay, now the way in which this device works is, okay, for a given DC voltage there is a given DC current plus a small AC current. Okay, and the relationship between this AC current and the DC current is, let us go back to this input characteristics thing, right? Let me just redraw it here. Let's say this is my VGS, this is my ID, okay, and as I mentioned, it is basically going to be a quadratic dependence. Let's say I am going to bias it here. Okay, let's say this is 0.45. Now I have a small sinusoidal signal riding on top of this bias, right? Now what will happen to the current here? If you zoom this region out, okay, this particular thing is going to look like pretty much like a straight line, okay, because it's a very small variation here, and if you kind of zoom it, you will see that the current variation with respect to that voltage can be thought of as a straight line, okay, because there is an infinitesimally small variation in the input voltage, and the current will also vary as the sinusoid. Okay. Alright. So this is the small signal approximation. So you have a device which is quadratic in its nature, but then when you apply a small perturbation or a small signal on top of a DC bias, the variation in the current is taken to be linear, and this transfer function is taken to be is a transconductance, right? Because you have dou ID by dou VGS, right, at a given VGS naught is what is taken as GM, which is called as transconductance. Okay, basically what we are saying is, what is the slope? Okay, by how much will the current vary for a variation in the input? It depends on the slope. So what is the slope of ID versus VGS at this VGS naught of, let's say, 0.45 volt? Okay, the slope changes as you move along this curve, right? So at a given DC bias point, what is the slope? Okay, and that slope is taken to be the transconductance value GM. Okay. Now, building the small signal model, so we can say that the input is a gate, and you have the oxide. The oxide is what? If you look at the thing, this is the oxide, right? The oxide is a very good insulator. So the current which is flowing in is basically zero. It is as good as having an open circuit. Okay. So the small signal model is that it has an open circuit gate. Let's say this is the source. Let's say this is the drain. Between the drain and the source, there is a dependent current source whose value is given as GM times VGS, where VGS is here. Notice I am writing small VGS because this small VGS is the small signal gate to source voltage. Okay. So in that example, this VGS is nothing but, okay, the small VGS is nothing but VAC. Okay. So here I told that VGS is given as VDC plus VAC. For the small signal model, you only consider the small VGS, which is equal to VAC, and this sets up a small signal current which is basically equal to GM times VGS. Okay. So therefore, let's say the Vin can be written as VDC plus VAC, and ID can be written as what? IDC plus GM times VAC. Okay. This is the fundamental relationship, and therefore this is how we understand the transistor. Now I mentioned that so this model is valid only in the saturation region. Okay. So VDS has to be greater than VGS minus VDS, and that is where all amplifiers will work. Okay. Now here we saw that there is a slope. Okay. There is some dependence on VDS. Okay. Which means that if you think of it, another way to denote it is to say that this current source has a shunt resistance whose value is R0, and this value of R0 is nothing but dou ID by dou VDS for a given VGS, the whole inverse. Okay. So dou ID by dou VDS, the whole inverse is R0. So it can be thought of as a ideal current source with a shunt resistor, and this is R0. So all of you guys should have learned these things and just refreshing your memory. Okay. This is your small signal model, and this GM, as I mentioned, is dou ID by dou VGS. So you can dou by dou VGS of, let's say, mu n Cox by 2 W over L VGS minus VTH the whole square, and you basically I will write three expressions. I want you to derive them. It's very simple to derive, but I don't want to spend too much time on these things. So you have three different equations. This is one expression. This is another expression. This is the third expression. All these three are equivalent expressions. If you just derive them and do some jugglery, you will basically get all these three expressions. Okay. You can see that GM is, here I have written capital VGS, which means that GM is a function of the bias voltage. Okay. This is what we should understand. The small signal model is valid only for a certain bias voltage. Okay. And the GM, as you change the bias voltage, as you change the DC bias, the GM changes. Okay. Even R0 will change. In fact, R0, if you differentiate this equation, which equation? This particular equation. Okay. If you find out dou ID by dou VDS, you will basically get lambda VDS. Okay. Sorry, lambda times ID. Alright. And 1 over that is basically 1 over lambda ID, and here ID is also their DC current. Okay. So as you change the DC bias, the DC current changes, and your GM value changes, your R0 also changes. This you must understand. Okay. Alright. Now this is all small signal model for a low frequency thing. Let us look at all the capacitors that are there. Right. Now let me draw the device again. This is your oxide. Okay. Right now I am only going to look at the capacitance in the saturation region. You can look at other textbooks to look at the capacitance in the other regions and so on. Okay. So let's just look at this capacitance. Okay. Now usually what happens is there is a little overlap of the oxide with the drain and the source regions. Okay. So you have what is called as the overlap capacitance. Okay. Now the channel is basically formed like this, right? In the saturation region, the channel will be something like this. Okay, which means that there is this capacitance formed between the gate and this channel, right? It's like a parallel plate capacitor. So you basically have one more capacitor. Let me just call it, the C channel. Okay, so you have a larger capacitor for gate to source, and you have a smaller capacitance between gate and drain. Okay, so basically, if you look at the device, you can say that there is a gate to source capacitor. So let me just redraw it a little better. You have an effective gate to source capacitance CGS, which is the combination of the overlap capacitance and the capacitance between the gate and the channel. Okay. Now you also have this overlap capacitance between gate and drain. Okay, CGD, right? Now, what else do you have? Okay, you basically have two diodes here, right? I think I have explained this before. This is P minus, which is grounded, N plus, which are at different potentials. These two diodes are reverse bias. Any reverse bias diode will have junction capacitance, and therefore you will have, if this is your bulk terminal of your MOSFET, okay, you will have source to bulk capacitance and drain to bulk capacitance. Okay. So all these different capacitances are there in your circuit. Okay. Now let us draw the small signal high frequency model. Okay. Now how is this high frequency model going to look like? Now between gate and source you have gate to source capacitance. Let's say this is GM-VGS, this is your R0. Okay. Now between the gate and the drain you have, this is your drain, this is your gate, this is your source. Now you have gate to source capacitance between gate and the source, gate to drain capacitance between the gate and the drain, and you have drain to bulk capacitance CDB, and you have source to bulk capacitance CSB. Now this is a model of the MOSFET. This is a small signal model of the MOSFET with all the capacitors also in the picture. Okay. Now with this we are ready to now start designing circuits. Okay. So if you need to spend more time on this, I will also put a link to my lectures from the previous semester where I taught a course on analog VLSI circuits. So I would have explained this in a little more detail. I just kind of had an overview now. So you can refer to those lectures. I'll put the link in the Moodle page. Already I had put one on CMOS device. So you can basically go and look at it, or I'll also put one more thing. Okay. Now let us start looking at the LNA. So LNA design. Now what are the design specifications that we have for an LNA? Usually the LNA interfaces with the off-chip antenna. Okay, usually antenna is on off-chip. Okay, and so you might have antenna plus bandpass filter, or sometimes you have antennas without bandpass filter. Okay, many of the cellular research receivers now are looking for are basically implementing solus receivers. That means you get rid of the bandpass filter totally. Directly the antenna connects to your LNA. Okay, so whatever it is, this is your chip boundary. Okay, this is on the chip, this is outside the chip. Okay, now because the trace lengths here are longer, the first main important thing is the input impedance should be matched to 50 ohm. Okay. So input matching is extremely important for your LNA, because if it is not matched, what will happen? All the power that is being received by the antenna will get reflected by the LNA. Nothing will go into your receiver chain. Okay. So input matching is very important. And secondly, as you know, noise figure. Right. the noise figure has to be as low as possible. And thirdly, what do we need? We need to have a pretty high gain, because if your LNA's gain is higher, then the noise figure contribution, the noise contribution of your subsequent stages are all decimated by the gain of your LNA. So you like to have as high a gain as possible. Okay. Now the other thing which is important is basically linearity. Okay. You remember we talked about IAP2, IAP3 and so on. Okay. So 1 dB compression point, receiver desensitization. So this LNA, so what can happen at the input of the LNA is you can have a huge blocker, right? This is basically the blocker, or in other words interferer, and you will also have a small desired signal. Okay. So what is usually required of the receiver or the LNA is that you should be able to detect this small signal even in the presence of large blockers. Okay. As I mentioned, for GSM, this blocker can be up to 0 dBm. Okay. And still you should be able to detect, I think, minus 90 dBm or minus 80 dBm. I don't remember the exact value, but something like this. Okay. Even though at a certain offset, okay, they give a certain offset. This will be the offset. So at a given offset, okay, even if you have a 0 dBm blocker, you should be able to successfully detect and demodulate a minus 90 dBm or minus 80 dBm input signal. Okay, so which means that the low noise amplifier also has to be quite linear. Okay, its IIP3 has to be high, its 1 dB compression point has to be high. Otherwise, what will happen? The LNA will compress and you will not be able to detect this thing. So linearity is also a very important thing. Okay. Now all these constraints, okay, and also one more thing, stability. What is stability? Your S11 should be always less than 0 dB, right? The magnitude of S11. Okay. And in microwave circuits, you also would have looked at the K delta factors, right? The Stern stability factor, where with the S parameters you have K given as 1 plus modulus of delta squared minus S11 mod squared minus S22 mod squared, where del is basically divided by 2 times modulus of S21 modulus of S12. I am just writing the equation. We are not going to go into it. I am just going to show you that there are these things which also need to be simulated. Okay. And we will look at a certain aspect where it can become unstable. So delta is given by that. So for unconditional stability, what do you need? Your K should be greater than 1 and delta should be less than 1. So this is what is called as the Stern stability factor or the K delta stability thing. For all values of input and output, it basically should be stable. Okay, if it is not stable, then your amplifier will become an oscillator. Okay, so physically, okay, if you take an amplifier, if it becomes unstable, what will happen is it starts oscillating. It will start oscillating at a certain frequency. You don't want that to happen. Your amplifier should stay an amplifier and your oscillator should stay an oscillator. Okay, so stability is also an important parameter. Okay, now all these things put together, you will have a power budget. Okay, you'll basically, what happens is typically your low noise amplifier will consume a lot of power. If you look at a receiver, entire receiver, the majority chunk of power will be consumed by your LNA, and the other power will also all be less. Mixer power, baseband filter, ADC power, variable gain amplifier, all these things will consume much lower power. The biggest chunk will be consumed by your low noise amplifier, and of course another thing that we always keep in mind is the area occupied. Okay, and we also look at bandwidth and things like that. Okay, so these are the parameters, these are the specifications that we need to be aware of when we start designing an LNA. Okay, now first let's look at the problem of input matching. Okay, in order to do input matching, we should first find out what is the input impedance, correct? So let's say we take an NMOS device, all right. Let's say, you have the source is grounded, so you have CGS, you have some CGD. Let's say we just put some resistive load here, let's say RD. You have some load capacitor CL. Now, always we model a certain load capacitor because the next stage input will also have what? A CGS, right? This LNA is not going to hang in thin air, right? LNA is going to get connected to the next stage. The next stage also has MOSFETs. And MOSFET input impedance is usually capacitive in nature, as we saw, right? So all that is modeled as some load capacitor CL. Now, when you have a common source amplifier like this, okay, you can try to find out what is the Y-in or what is the Z-in, okay. Now, I am not going to derive that. You can take the small signal equivalent circuit, put that and do the whole derivation. Now, what you will see is basically the real part of Y-in is going to look something like this. RD into, let's say, CGD omega squared and CGD plus GM RD CL plus CGD divided by RD squared CL plus CGD the whole squared omega squared plus 1. Okay, so we are not going to derive it and also not going to ask you to derive it in your examination, but the derivation I think will be in the textbook, so you can always derive it and figure it out. Of course, it's going to be a little messy. Looking at the expression, you will know. So the real part of the impedance is going to look something like this. You have omega squared in the numerator as well as in the denominator. Okay, and the imaginary part of Y-in, if you derive for this, you are going to get something like this: CGD times omega RD squared CL into CL plus CGD omega squared plus 1 plus GM RD divided by RD squared CL plus CGD the whole squared omega squared plus 1. Okay, so pretty messy expression. So basically how you derive it is you draw the small signal equivalent circuit GMVGS, and you have, I think they have not considered R0 here. Many times you'll consider R0. You'll have CL, you have RD, you have CGD, you have CGS. Okay, this is grounded and you are trying to look at the input impedance. Okay, so how you do it is basically you will say, I am going to put a test voltage source, okay, VT, and I am going to look at IT. Okay, so VT by IT, or rather IT by VT, Y-in is nothing but IT by VT. So you can derive this and you will basically get something like this. Okay. Now what do we see here? What is important is the conclusion. Okay. A derivation, anyway, if you spend some time, you will be able to do it. Now what do you see? Although we say, the first important thing that I want you to notice is that although we say that the input impedance of a MOSFET is capacitive in nature, okay, we see that there is also a real part. Okay, there is a real part which is happening, and the reason is, of course, you can derive it and see. An intuitive way of understanding is that this capacitor CGD, right? This capacitor CGD sees a certain real part here, which is RD to ground, right? It is RD to VDD, but for a supply is basically a AC ground, small signal ground, right? So this CGD in series with this RD is basically going to do what? Some series to parallel transformation, and so when you are looking from the input, there is some series parallel transformation happening, and you are going to look at some real part. Okay, so this real part is extremely negligible at lower frequencies, which means it becomes very, very high at lower frequencies. Okay, so it is parallel, it is Y-in, right? So okay, sorry, this is Y-in. Y-in becomes very high at lower frequencies. In other words, sorry, Y-in becomes very low at lower frequency. In other words, the input impedance, the real part is very high at lower frequency, which is why you say the input of a MOSFET is capacitive in nature. But as omega increases, the real part of Yin also increases, which means the real part of Z impedance starts dropping. So the real part starts coming into the picture as you go up in frequency. So when you reach RF frequency, the real part starts showing up. Okay, and same way, of course, you have a certain imaginary part. Okay, and you also see that the real part is now basically a function of the frequency. So as your frequency starts increasing, the real part starts becoming more and more significant. Okay, you start seeing a lower real part as you go for lower real resistive part as you start going up in frequency. In other words, what you are seeing is the input impedance is like a certain real part with a imaginary minus jx part, or let's just say minus jb part, plus jb part, and a certain conductance g. Okay, and this conductance starts increasing as omega increases. Okay, this is our conclusion. But even then, the real part of this thing is still in the range of kilo ohms inverse. Okay, so it will be in the order of milliohm, millisiemens. Okay, the real part of Yin at, let's say, lower gigahertz frequency is going to be like this. So the moral of the story is that the input impedance of your MOSFET has a certain real part, but that is nowhere close to 50 ohms. Okay, if you look at real part of Zn, let's say it is in the range of kilo ohms. Okay, so it is nowhere close to 50 ohms. So we have to do something to establish a 50 ohm at the input. So how do we do that? We will see in next class. Okay, any doubts, any questions so far? Any concept you want me to explain again?
Equal to 50 that RF frequency, no?
Sorry,
can you repeat? Zin.
Sorry?
So real part of Zin not equal to 50 at RF frequency.
Yes, at RF frequency.
Okay.
Okay, it's not equal to 50 ohms. So let's say 1 gigahertz, 2 gigahertz, and so on. It's still at in the range of some kilo ohms range. Let me just say, gigahertz, lower gigahertz range. Okay. So this is how it behaves. Of course, at lower frequencies, it is even more higher. Okay. So typically, if you are looking at kilohertz, lower megahertz range, this real part of Zn will be in the order of some, mega or 10 power 8, 10 power 9 ohms kind of thing. Okay. Any other questions, doubts? Okay. So with this, we'll wind up today's class. So thanks everyone and have a nice day.